First, I would like to thank Alluxio for hosting this summit. Second, I would like to thank all of you who joined. I'm Koen Michiels, CEO of Datasapiens, and
I'm Juraj, Pohanka, CTO of Datasapiens.
We're looking forward to sharing our learnings with you. To that purpose, we are aiming to talk through the following agenda today. We will start off with a brief introduction to Datasapiens, who we are and what we do, followed by a high-level overview of our infrastructure journey. We will then deep dive into the observations whilst implementing Alluxio, which we will aim to quantify better through a reproducible example using the TPC-DS dataset, and conclude with some general recommendations around cloud data lake architectures. Now about Datasapiens. We were founded in 2014 by combining experts from technology, data science, and business experience, as we believe that it is at this intersect that successful data products are created. We have 3 key products operating in 15 countries and in just over 100 million records weekly. Our tools help to turn data into profit. The 3 products that I described earlier are the following: personalized offers, business insights, and brands insights. Personalized offers are all about increasing customer engagement, sales, and margin from your customers. We introduce a simple plan-do-review process to continuously measure and improve the loyalty lifecycle of your customers. Business Insights is our BI with embedded insights framework that helps you to become data-driven. Brands Insights is our platform to drive supplier collaboration and commercialize your data assets. We are proud of having the following users: retailers such as Marks & Spencer's, Macro, and Circle K, with FMCG suppliers such as Coke, P&G, and Colgate. Pharmacy chains such as Phoenix, Benu, with their pharmaceutical suppliers such as Teva and Sanofi. In addition, we also have a partnership with Nielsen in Asia. That's enough of an introduction. To talk you through our infrastructure journey, I will be handing you over into the ever-capable hands of our CTO, Juraj.
Thank you. So our infrastructure journey. Roughly 1.5 years ago, our entire data warehouse infrastructure was based on Redshift. We had several running Redshift clusters, which were powering all our ETL processes, our Datasapiens platform, and many internal analytical tools. This setup had the benefit of simplicity. Redshift has a nice and intuitive UI, and all responsibility regarding maintenance is done by AWS. Redshift is a transactional distributed database, hence it is a good choice when doing traditional OLAP-oriented data warehousing. However, there are also a few shortcomings. Redshift has a storage compute coupled architecture, hence one cannot scale storage and compute independently. Another specific attribute of Redshift is the query compilation for achieving higher performance. For data workloads with more or less static queries, this is an excellent feature, but for ad hoc data analysis, this becomes a performance bottleneck. Moreover, Redshift is AWS specific, hence we had a vendor locking of a crucial part of our infrastructure. To address the requirement of independent scalability in both storage and compute dimensions, we had decided to migrate to the Hadoop ecosystem. This vast open source ecosystem provided a pluggable, compositional data warehouse architecture made of tools where each tool had a specific purpose. These are the attributes that we were looking for. It is a common pattern to choose Hadoop HDFS as a distributed fault-tolerant storage, Hive for creating a SQL layer on top of HDFS, Presto as a distributed query engine, and Spark for ETL. We have decided to go with this set of software components, except for HDFS. There, we decided to use directly S3 as a data storage. We would use Spark via EMR, but all other components we would have in containerized deployments. Our Presto clusters would then be accessed by our Datasapiens platform, as well as by all our internal analytical tools. Via this architecture, we would have storage compute separation and would have a greater query performance due to zero query compilation times. However, this architecture had one unforeseen flaw. Using S3 for direct data querying resulted in S3 API costs greatly exceeding our expectations. Due to this issue, we had to revise our architecture and come up with a feasible solution. We still wanted to have S3 as our single source of truth data store, but we knew that we needed to be able to throttle the number of requests to S3. Among our initial considerations was using Hadoop HDFS as a simple data orchestration layer sitting in between S3 and the data processing system. This would, however, require running synchronization jobs between HDFS and S3. We were also aware of Alluxio, mostly due to its capability of storing data in a multi-tiered way, with the fastest tier being in-memory storage. Alluxio has the functionality of checking the under-file system for changes, hence eliminating any needs for external data synchronization. After several social proposals, we decided to go with Alluxio. Pretty soon, after deploying the refined architecture to production, we could see the benefits. The query performance has increased greatly, and the S3 API costs have dropped to a negligible level. Today, we run several co-located Alluxio Presto clusters for our clients, where from individual clients, we have hundreds of users. Our observations. Here we will describe how we observe the significance of S3 API costs when directly querying from S3. When we were designing our Hadoop-based infrastructure, we needed to understand each of its components. More specifically, we needed to fine-tune the Presto cluster in order to achieve a reasonable performance under a given workload. Apart from the configuration of our software stack, we have also designed our data warehouses. When using Redshift, we use the common star and Snowflake schemas for the design of the table entities. In our new approach, we wanted to migrate to a more OLAP-based model in which we would keep all entities rejoined in few OLAP cubes. This would minimize the need to do extensive joins on the fly. And in the process of choosing a feasible pair of software configuration and database design, we conducted several performance tests on our first Presto cluster. The cluster and all additional components were deployed in a Docker Swarm cluster. We used our internal performance tools, what would send query request to Presto, which would then send request to S3 API. And it was during this period of performance tests when we detected a dramatic increase in our S3 API costs. The following AWS cost chart depicts the daily S3 API cost made by our Presto cluster. Days with higher costs correspond to the days when we did the performance tests. Other days with a seemingly minuscule S3 API costs were the days when we were revising our data warehouse designs or the configuration of the software stack. We have summarized our daily performance test query loads into the following table. We tested a total number of 23 queries within 1 year of client retail data stored in few OLAP cubes in Parquet format, all partitioned by the time range of 1 ICE a week. The next table depicts the comparison of S3 API costs with the infrastructure costs for the performance tests. We can also see what percentage of the total cost the S3 API occupy. And in the majority of the cases, this is above 50%. Regarding the workload, we tested different concurrency levels ranging from 1 to 150 currently running queries. As mentioned before, using Alluxio solved the issue with significant S3 API costs, reducing them below $1 a day. For a better quantitative understanding of S3 API costs when querying directly from S3, we have made a simple reproducible test on the TPC dataset. For such test, we have used 2 separate clusters. One was an Alluxio Presto cluster using Presto SQL, using production, and the second was an EMR cluster with PrestoDB. The reason why we could do this is that regarding request counts to S3 API, Presto SQL and PrestoDB are equivalent. The second cluster also serves as a reference point for testing S3 API costs of AWS provisioned Hadoop stack. We have used the TPC-DS dataset with a scale factor of 100, which was stored in an S3 bucket. We have executed each query for a TPC-DS suite with the exception of query 72 due to low query times. Each query has been executed exactly 10 times, and we have executed them in a sequential manner, thus with concurrency level equal to 1. For measuring the per query request counts to Alluxio FS, we use the files info's got logical operation and the get file info RPC. We use the total count and cost per request type. The following table contains the 10 most request expensive queries. We can see that the average requests via the file info's got operations for the first 4 queries is about 100,000. To put these numbers into a better perspective, our TPC-DS dataset has a few tables and these that are partitioned by either a time range or by a specific grouping of products. The dataset has overall 12,000 files. There we observed that these queries require 5 to 10 times higher requests than what was in the total number of files. This implies that Presto sends several requests to the same set of files during query execution. And these 2 tables are the cumulative request count and the total S3 API costs per each request type. As you can see, the cumulative S3 API costs are quite negligible. And here we have the cumulative S3 API costs, request count, and costs per each request type. And for your reference, we have included the S3 API cost estimation per query, but let's move to the overall cost comparison. Here we see the comparison of the infrastructure and S3 API costs for both clusters. As it is apparent, Alluxio makes a huge difference in resulting S3 API costs. When used, Alluxio reduces the S3 API cost to approximately 0.58% of total and is negligible. If not used, it makes around 48.83% of the total costs, so nearly half of the cost is being spent on a small service within a large service set in AWS. So, a more general question. What do these results imply for generic Delta Lake architecture? Looking at the pricing models of the 3 largest cloud providers, hence AWS, Azure, and GCP, we can see that they are very similar to each other. Consequently, we can expect similar levels of cost differences between data lake architectures with and without data orchestration layer. This claim, however, still needs to be verified for the case of Azure and GCP. Real-life production data workloads exhibit a far higher storage and compute demands than the TPC-DS example workload that we have analyzed in terms of S3 API costs. Therefore, the cost reduction in these workloads will be far more significant, and deploying Alluxio in them will be even more beneficial. So to summarize our findings and learnings, it is vital to implement a data orchestration layer between the cloud storage service and the target data processing system. And for such purpose, Alluxio is a very suitable data orchestration solution. Here we also post a few useful links. The first one is the GitHub repository with the complete test results. The second one is our DZone article, where it describes a little bit in more detail our procedure of the experiment, and nonetheless also the company website. And with this being said, I would like to thank you for all of your time and your attention, and we are eager to answer any of your questions. Thank you.